With XPS, we have the big advantage that the noise is understandable. It's meaning the noise is equal to the root square of the intensity. So we can quantify the statistical uncertainties with a very good precision and in an easy way. Of course, this don't take into account all the kind of uncertainties, like if you don't the choice of the background, the type of the background, and the transmission function calculation. So that is some other kind of systematic error. But in terms of statistic error, we could be very precise. With computer, we can reproduce a measurement for 400 times in this with CASA, and we can calculate it, the standard deviation of the quantification. So the first thing to do, we load the data, and we done on these conducting samples for measurement. That is a conducting diamond, so we have an advantage, and we don't have some charging effect, so it will make the job to make quantification a little bit easier. Okay, first thing that we have to do is to use the uncertainty tools. We need to verify that the uncertainties follows the Poisson law, that is the root square of the intensity. That is what we're doing, and this meaning when we use the background regressive that on a linear region, that we have to be around 1 for the residual, and that is independent, and that have to be independent of the intensity. It's not perfect, but it is close enough to work. So now we delete this first step background, and we will create for the different we will create the background for the different XPS process, and we have on these samples. So first we check and we have the appropriated sensitivity table, and now we can doing the background using the tools, and we can find pick, and we remove the natrium. We have no natrium, and we create region. Okay, and we can see that we have no boron because, as you've seen, it's a little bit too small or too shifted to be accepted to be created by the program. So the first thing that we have to do is to change the background, because CASA remembers the last background that you have used. So now we will use the 2-card background with, in terms, and you have a good statistic, the best things that we can do from my point of view presently. So we do again a create region, and this time all the background will done by default using a 2-card background and same parameter for each region, and average of 1, meaning that we take left and right 3 points to make so exactly position limit of the background. So now we know that we have to add the boron region. Will we do it now? And when we creating, we have to take or to add, to say to the program that is boron. So that is what we use in the first row on a column. And also, if we want to do it well, when we have a solo background, and we make a background on a so short region, is, from my point of view, definitely better to use the linear background. It's have no sense to use a tool like the 2-card background when you have a solo intensity relative to noise. We choose an average of 2, meaning 5 points right and left. That will give us a better a better knowledge of exactly position of the background. Of course, the choice of the limit could be discussed. It's not never easy to find a perfect solution. I try to do something realistic. And now, okay, it's done for the first samples. So we want to propagate to other samples. It's done, and with this display we can see directly the 4 samples results. Now we will be check region by region, the oxygen 1S first, and we adjust the display windows to have a good viewing, and we adjust the limit left and right to have a good choice, and the good choice have to be, in an ideal case, if it's possible, work for all the measurement together. It's meaning when we will modify one parameters, we will able to propagate to other one in an easy way and have a kind of self-consistent measurement. It's important. If you change too much calculation, background parameters between your different sample, you're starting to induce some systematic error who is not good. If it's possible, it's better to try to be homogeneous on your data treatment way. But it's just a suggestion, it's not an absolute rule. Okay, I am satisfying by this. So let's go to the next element and try to make it better. Okay, for carbon is done too, so we'll move to the next. Chloride. Okay, again, due to the fact that we have a very low or very poor background and intensity of the peak, I definitely prefer in this case to use a linear background. This is more stable. Again, we verify that for each measurement, then the choice are good. As you can see, we have practically we have no chloride for the last sample and very low intensity for some other one. So the idea also to make statistic uncertainty, that meaning that the statistic uncertainty have to show us that the quantities that we measure is insignificant if we make background when we are practically no intensity. So again, we done it. Now we have seen in one click practically we have the statistic error for each sample. And there is also another advantage when we use this. You can play, for example, with the average. The average of your left and right background limit determination to reduce your uncertainties. You have to do it in a reasonable way. Sometimes you win, sometimes you don't win, But now we have reduced the uncertainty error on oxygen. It's meaning by the fact that everything is correlated, uncertainty on one element will induce uncertainty on the other one, will improve the general uncertainties. Of course, sometimes it's not necessary. If you try to improve of the carbon, the intensity is so high, and you don't need to have many points, to have too much point left and right, to have a good knowledge. It will not give you any improvement. But that is also uncertainty a very good way to try to extract more reliable information of your data. Thank you very much for your attention.